This presentation is about the analysis of realistic DS-OCDMA VLC for V2V communication using Opti system. This project has been realized in cooperation with my supervisors, Dr. Younes Zwin and Dr. Madini, who I them to thank very much. The plan of the presentation goes as follows. At the first stage, I'm going to provide definition for the terms that are included in the study. V2X communication, VLC, OCDMA. First, what is V2X communication? Second, what is VLC? Third, the OCDMA structure. After the definition part, we shall move to our core study, that is realistic DS-OCDMA V2X communication using Opti system. And finally, where will be a short conclusion, and we will also have a look at further works about the same topic. First, what is V2X communication? It's a technology that allows vehicles to communicate with moving parts of the traffic system around them. Second, what is VLC? VLC is a data communication variant which uses visible light. We normally use long radio waves in telecommunication. However, this technology uses a visible spectrum. Fluorescent lamps are used to transmit signals. Now, I'm going to define DS-OCDMA. It refers to direct sequence optical code division multiple access. In this structure, each user operates on OOK modulation to transmit an independent and equiparable binary data upon an optical channel. A sequence code is impressed upon the binary data by the encoder. The sequence code is defined to each user to be able to extract the data at the end level. All that I have mentioned so far will help me to introduce our proposed system. In this system, the optical orthogonal codes OOC that are generated by a MATLAB block in simulation with Opti system are used to simulate the usefulness of DS-OCDMA VLC system for communication V2X. The objective is to generate the sequence codes corresponding to each user and implement them in Opti system simulator using MATLAB. The encoded data of each user will be transmitted together in a signal color using LEDs. The empty space between the transmitting and the receiving ends represents the transmission channel, where the colors shall be mixed at the receiver level. We can spot the data of the desired user that uses a conventional correlation receiver. In the slide to come, we will detail the different blocks make up the system. Let's describe the transmitter and what happened at the transmission level. Our system proposed consists of multiple users separated into a number of groups. Within each group, the users share one wavelength. As we can see in the figure, optical orthogonal code are generated by the MATLAB block. 5 users are supported in the code we have used. The encoded data are then sent all together in a wavelength using LEDs. All the transmitted generated lights will be mixed and transmitted in free space then receive it after propagating a certain distance. In this slide, figure the NRZ coding at the transmitter level. At the left, we can see the NRZ code generated, while the figure at the right show the signal after NRZ coding. Mind you that our signal is generated by a MATLAB block in combination with OptiSystem. The transmitted signal at the input of each cluster can be expressed by the following equations. The data of the user K is represented by this equation, and the last term in is the signature of each user. It makes it possible to easily distinguish the desired user from other users. We shall consider the free space between the transmitter and the receiver as a transmission channel. In the simulation, we have defined the distance between the two ends as 100 meters. The performance of the system shall be affected by noise sources such as the ambient optical noise and the thermal noise, which can be expressed as we can see. At the receiver end, the received signal is correlated with the code of the desired user. At the stage, the multiplier output signal is reformatted through an integrator to evaluate the total power per bit. The output signal presents the decision variable. Later, the decision variable will be compared with the value of threshold S of the decision-making blocks, so as to make the estimated data. We can see here the conventional correlation receiver when the signal is integrated in a bit interval in order to obtain a decision variable. The second term in the last equation represents the interference due to the other user, MAA. In the figure at the right, we see our signal after begin subject integration. The value A and B represent respectively the threshold 1 and 4. We can see that the performances decreased when the threshold goes up. There is a trade-off between the threshold and the performances. The results show that our system has relatively the same performance as the theory. To sum up, this presentation was about a simulation study of OCDMA VLC system. The simulation was realized by co-simulation of OptiSystem with MATLAB. It has been shown that the feasibility of our suggested system is possible, as it seems to have the same realization as the theoretical part. Our objective is to have this work realized in reality in the near future, and thank you for your attention.
Hello, today we will introduce our summary article called Optimization of a V2V Communication in Cognitive Radio Context. So on the plan, we will start by an introduction, then talk about vehicular networks, cognitive radio network paradigms, then vehicular networks VANET architecture, and vehicular communication evolution, and in the end, a conclusion. So to increase safety in smart cities, especially in vehicles. So a new technology was appeared called Internet of Vehicles, which can be established on three forms of communication: V2V, V2X, and V2I. The existing V2V are based on single radio and are inefficient and unreliable, especially in the hilly area due to low SNR and partial coverage. Now they are based on new technique of communication called cognitive radio, which are the smart layer to the medium access, with growing interest in using cognitive radio technology in wireless communication system for vehicles. So it is envisioned that future vehicles will be CR enabled. This article presents the fundamental knowledge about the cognitive radio. We will present different cognitive radio network paradigm. So, since their appearance, the VANET has greatly developed so many standards, applications, and routing mechanisms which address the specific of this new class of networks. And the Internet of Vehicles has become an important part of the Internet of Things and smart cities being proposed and developed worldwide. Thus, EOV goes beyond telematics and Adhoc vehicles network and the integration of vehicle sensor and mobile device into a global network to enable the delivery of various services to transport and vehicle systems and to people on board and around vehicles. For the vehicular networks, so intelligent transportation systems ideas integrate new information and communication technologies to applications in the field of transport to improve them. Now, vehicular ad hoc networks or VANETs are among the ETS. Their mobile nodes called onboard units or OBS. Many studies in this field consider VANETs to be mobile ad hoc networks emanate with high mobility without taking greater account of the constraint of their environment. The VANET terminology groups together three different architectures which will be presented below. So the first is V2V or inter-vehicle communication, the second V2I or communication between vehicles and infrastructure, and the last one V2X, vehicle to anything, also called hybrid, that combine both of them, V2I and V2V systems. Now, vehicle to infrastructure or V2I use a roadside unit deployed on the side of a road at regular intervals. These equipments carry out the establishment of communication between infrastructure and vehicles. It is a centrally managed network architecture administered by the managed route network that plans and optimizes communication traffic between connected equipment. Now, for the vehicle to vehicle or V2V, based on the links communication between OBUs, these OBUs collaborate in a decentralized architecture to create an ad hoc network. It can't stand the breakdown of a network node, but it still requires a sufficient number of nodes within communication runs so that communication can be established. The implementation of the V2V architecture uses distributed routing algorithm whose performance levels are for nature more complex to predict compared to those used in a centralized architecture. For the V to anything or V2X, it's called also a hybrid. It's combined both V2E and V2I. In this operation mode, the two systems must complement and cooperate in order to ensure continuity of service. The implementation of V2V architecture uses distributed routing algorithm whose performance levels are for nature more complex to predict compared to those used in a centralized architecture. Now, physical constraint inherent in the communication medium. So the propagation of radio wave emitted on a medium is subject to attenuation phenomena and distortion. Multiple paths inherent to the reflection, refraction, and diffraction on the obstacles encountered by the signal in very varied propagation environment, urban that contains many buildings and route, suburban and motorway intersections. The use of the communication medium for vehicle application requires the adoption of a radio technology whose medium access control MAC layer ensures the sharing of resources, communication limits in terms of speed and bandwidth, and access to the communication medium, sometimes competing with different nodes of the network. According to the number of nodes within a range and the number of access requests, the propagation condition of signals mentioned above, transmission delays, and data loss of very importance can be observed in a VANET. Now, constraints imposed by the route context. So the nodes of VANETS are characterized by their high mobility. Node speeds vary from 0 km per hour, sometimes at more than 130 km per hour. Traffic direction can be sharp at intersection or opposite in urban, peri-urban, or two-way highway circulation. The variation of this mobility induced by those of speed over time and interaction between vehicles are also responsible for the strong topological variation in the network communication. The variation in vehicle density over time is significant and dependent in particular on the type of route and traffic, and the end congestion phenomena of bundle occur in the case of high density of vehicles due to limited network communication. So the too low density of vehicles will cause intermittent and sporadic connections, which may prevent information from being released. Now, scaling up, the number of sensors on board vehicle and the penetration of communication systems within the auto market will increase year after year. The amount of information collected and exchanged within a VNet will follow the same trend. So modeling and evaluation by simulation of a routing protocol adapted to the VNet must include scenarios allowing to anticipate the passage to the scale in terms of number of connected nodes and of flow of data exchange. Now the IEEE 802.11p. So the IEEE 800.11p standard is an amendment to the IEEE 802.11 standards that the IEEE Task Group TGP began to develop in 2004 for wireless access in intelligent transport system. The IEEE 800.11p physical layer use the same signal processing mechanism and the same specification as in the 802.11a standards, with however some modification to adapt it to vehicular environment. The MAC layer of the IEEE 802.11p standard is equivalent to the EDCA technique of the 802.11e standard. In EDCA, messages are classified into 4 access categories. Now, cognitive radio network paradigm. Cognitive radio network paradigms. Underlay paradigm. So require that the transmission between primary and secondary is established only if the interference generated by the secondary transmitter at the primary receiver is below an acceptable threshold. Rather than determining the exact interference it causes, a secondary user can spread its own signal over a very wide bandwidth such that the interference power spectral density is below the noise floor at any primary user location. The overlay paradigm, the secondary transmitter has the primary user transmitted data sequence message at an encoded code book. In the case of following a uniform standard of communication by primary users based on a publicized code book, the primary user could broadcast their code books periodically. Data sequence may be extracted by decoding it at the secondary user's receiver. The last one is the Interweave paradigm. The Interweave paradigm is based on the idea of opportunistic communication. So the idea came about after studies showed that a major part of the spectrum is not fully utilized most of the time. In other words, there exists temporary spectrum whole space-time frequency void in licensed and unlicensed bands. So vehicular networks modelization ad hoc VANET. Now existing ad hoc network are two. VANETs created in 1999 responsible for standardizing routing protocols based on IP technology. For ad hoc network refers to the network without infrastructure in which all stations can be mobile. The proper name VANET is sometimes used as a common name to designate an ad hoc network, especially in English-speaking countries. VANET, a form of implementation of the VANET, very inspired by it, allows vehicles to communicate via security alert messages sent between them by a communication system by node. Each node is able to manage and organize a set of information sent by a vehicle in the area near the danger. Now, vehicular networks architecture. So routing techniques. We have anycast routing. In the anycast communication mode, the information packet from the sending node are sent to a single node chosen from among the nodes of a destination group. Unicast routing packets are transmitted to the address of a single node if this destination node is out of the radio nodes of the transmitting node. One or more delay nodes resend them until they are a scope of the address node. Broadcast routing the packets are transmitted to all the nodes of the network. Each receiving node then redirects them so that they reach all the nodes of the network. And multicast routing, the packets are transmitted to a group of nodes. So when this group of receiver nodes is defined as a function of the geographical position, so it's called geocast routing. So it transmits data to all the nodes located in a given geographical area. Now, components and architecture of a VNS. The architecture of VNS consists of three main components: UI application units, OBUs onboard units, and LSUs roadside units. I and OBU are used for consumer service and installed in vehicles. LSUs act as a router to provide these services to moving vehicle networks nodes in the network via the IEEE 802.11p standard. The onboard units are used for IP mobility management, data processing, and collection. Application units are separated devices or can be integrated with the onboard unit used to communicate with the onboard unit. Roadside units are installed and deployed on the roadside with radio coverage for vehicles. Dedicated short-range communication (DSRC) is used to provide communication between vehicles, and the IEEE 802.11p standards is used between other roadside units and onboard units. Now, this is a screen of the components and architecture of VANETS. Now, vehicular communication evolution. In recent years, researchers, governments, and the automotive industry have become interested in VANETS, where several ITS applications have emerged, not only for safety applications but also for comfortable applications. Several research and development projects on VANETS have been launched: secure vehicular communication, CVCOM, cooperative vehicle infrastructure system, SafeSpot, CarCode, safety relating cooperative cyber physical system, SafeCop, and other projects. So now, to conclude, so in the paper we presented the vehicular networks with different architectural advantages and constraints illustrated in the research project launched for the VANET. The aim of our research work is to improve and optimize the V2V communication by analyzing and studying a variety of communication protocol in correlation with the constraint of intelligent communication systems, latency, bandwidth, mobility, and power consumption. So, thank you.
Hello everyone, I hope you are doing well. I'm Mohammed Boutelin, professor from Sultan Moulay Slimane University, Morocco. First of all, I would like to thank the organizing committee for accepting our work to be present in the 7th edition of the International Conference on Optimization and Applications. I will be present our work entitled Use of Docker for Building Containerized NS2 in Case of Multiple Interface Multiple Channel Communications. This work is carried out in collaboration with Mr. Hassan Fawzi, Mr. Ridwan Hamzawi, and Mr. Belaid Bouikhaldi. As for our plan of this presentation is as follows. First, we discuss the background and objectives. Then we follow up with the methodology followed and the proposed model. And finally, we will conclude with results and discussions. The work in this paper is to provide a more generic solution which based on containerization technology, allowing the researchers to have complete flexibility when using the configuration of multiple interface, multiple channels scenarios. By applying our solution NS2 and multiple interface, multiple channel, the researchers will be able to run their simulations on any environment without the need to install and configure the NS2. The major goal of NS tool is to use to support network research and education in terms of protocol design. It was based on C++ language and provides the simulation interface to OTCL and an object-oriented dialect of TCL, but the mechanism of multi-interface multi-channel does not integrate into this simulator, so the researchers need to develop an extension of these tools to address this issue. This implementation is not easy because NS2 has a lot of file written by C++ and OTCL, and this implementation needs a grant work. Therefore, in order to save more time and energy of the users, we opt to do containerization with Docker. In case of using ODB protocol, these tools will take into consideration the multiple interface, multiple channel mechanism. This slide deals the AODB protocol. In AODB, the root discovery mechanism is similar, as we are having in dynamic source routine, but roots in routine table are deleted when not used for a long time, even they are valid roots. The model of this architecture contains routine agent, link layer, address resolution protocol, interface queue, medium access control, network interface, and channel. In our model, we used NS2.35, therefore to support multiple interfaces, and we modified the architecture as shown in the figure. In this slide, we discuss the adding multiple interface multi-channel to NS2. To support multiple interfaces, we modified the architecture, so each node has a fixed interfaces that is assigned for a long periods of time to a channel, a switchable interface that is dynamically assigned to a channel for a short duration. The roles of node transmission in this new architecture as follow. If the node X wants transfer data to node Y on channel 3, the switchable interface of X is switched to channel 3 before transferring data to node Y. If the switchable interface of X pointed at the channel 3, there is no interface switching. So, what is the virtualization? The virtualization is the process of creating a software-based or a virtual version of something, whether that is compute, storage, networking, services, or application. And what makes virtualization feasible is the hypervisor. This hypervisor is a piece of software that runs above the physical server or host. There are two main types of hypervisors. Type 1 hypervisors run directly on top of the physical server. They are also called bare metal hypervisors. Some examples would be VMware, Microsoft Hyper-V, or open source KVM. Type 2 hypervisors run on a host operating system, as shown in these figures. In our model, we used the type 2 of hypervisor based on Docker engine because they are simple to run, install, and do not require any special hardware features. This type is based on containers, which are completely isolated environments, and they are their own process for services, their own network interfaces, their own mounts, and they all share the same operating system. So the first thing we must do is to create a file named Docker file. Then define in it the image that we are going to use as a base and different instructions necessary for deploying the NS2 multiple interface multiple channel. When we use the configuration files, it is possible to build our images reading instructions from Docker file. This file shows some lines from this file. Install NS2 and implement multi-interface multi-channel architecture of mobile nodes is very difficult and take a lot of time to make the necessary changes in source code of this simulator. Therefore, to overcome these problems, we proposed in this paper to use Docker for building containerized NS2 in case of multiple channel and multiple interface communications. By using our container, we can decrease time of deploying these tools and make it run on any environment without need to install and configure it. The work is not limited to EODV protocol, but can also be extended to other protocols such as DSDV, DSR, TORA, OLSR, etc. Thank you for your attention. Welcome to any question.
Hello everybody, my name is Zakaria Sabir. I'm a PhD student from IEEE University in Kenitra. Today I'm going to present our work entitled Connected Vehicles Using NDN, Security Concerns and Their Main Challenges. The outline of our presentation is as follows. We'll start with an introduction and we'll talk about VANETS, Vehicular Adhoc Networks, followed by the named data networking, and we will talk about the security problems and their main challenges in applying NDN to vehicular networks, and we will conclude the presentation. In the last decade, manufacturers discussed different conceptions and notions such as intelligent transportation systems in order to achieve road safety and comfortable driving. Today, a variety of technologies are already deployed and vehicles can now use navigation systems, connect to the network, and run different applications. In addition to the mentioned services, manufacturers and research communities aim to achieve vehicle-to-vehicle and vehicle-to-infrastructure communications in order to enhance road safety by engaging alerts and safety messages between vehicles and roadside units. Nevertheless, vehicular ad hoc networks bring many characteristics such as high connectivity and dynamic topology, which makes the current TCP/IP inadequate for V2V communications and faces various technical difficulties. Named data networking, which is a candidate architecture for the future internet, appears to be a promising solution to succeed effective vehicular communications. In this work, we aim to give importance to the security concerns that may be faced when applying NDN to connected vehicles environments. For all the previous studies on security, the majority of them did not consider the characteristics of VANET. Therefore, the primary motivation of this work is to analyze security concerns in vehicular communications from the point of view of NDN. Vehicular ad hoc networks are a specified case of mobile ad hoc networks, MANET, where the nodes are either the moving vehicles or the fixed roadside units. A vehicle can communicate with another vehicle, with the infrastructure, or with anything, which is called V2X. We will present in the following some features special to VANET along with the security requirements, changes in the topology is a characteristic of VANET, where the velocity of vehicles can reach 200 km per hour, thus fast movements and frequent challenges of the topology characterize vehicular networks. Another characteristic is elevated processing capacity. Vehicles today are capable of providing powerful sensing, communication, and processing capacity to help road users to make adequate decisions. Vehicles can assemble, interrupt, and interpret and analyze data. Anticipate movements. Generally, the mobility of vehicles is defined by the routes and the highways. They are repeatedly connected to the equipment on the roadside, such as traffic lights, roadside units, and panels, etc. To ensure the good functioning of intelligent transportation systems, the communication and information sensitive information about the drivers of or their vehicles in the network must be secured. Hence, VANET should assure, as any other network, these security requirements. The availability, it means that the network functions well and information is always available. In the confidentiality, it involves regulations that restricts access to a set of resources. Integrity means that the data exchange between nodes over the network should not be altered or corrupted. And the authentication means that the identity should be verified between vehicles and roadside units, and data should be generated by an authentic user. And the last one is the non-repudiation, as the sender is previously known from a satisfying authority. He can't decline to send a message. Named data networking is a well-known information-centric networking instance that has been proposed as a promising future internet architecture. It presents a new communication concept based on content-centric. The packets are forwarded to the network based on their name prefix instead of IP addresses. Hence, it focuses on what to send rather than where to send. NDN uses two new types of packets, which are interest packet and data packet. And whenever a consumer wants to get a particular content, he broadcasts an interest packet over the available network interfaces. The routers will use the name carried by this interest packet in the forwarding process. In order to process interests, every NDN router maintains three structures: the CS, which is the content store that caches copies of incoming data packets in order to serve forthcoming interests; the PIT, which is the pending interest table that saves every forwarded packet which still unsatisfied; and the FIB, the forwarding information base that helps to forward interest packets to the eventual data sources. Nowadays, the network security is provided by keeping communication channel secured. On the contrary, and since NDN focuses on the contents instead of their original sources, it presents a new security approach that is based on securing the content itself rather than securing the transmission medium. This is done through a signature generated using the data producer's cryptographic key and carried by each data packet. Data signatures are required so applications cannot drop security. This approach may fix diverse problems that have been damaged the current internet infrastructure. However, NDN still has security concerns that need more investigation. There are basically two categories of attacks that require further research. The first one is the cache poisoning attack, where attackers disseminate fake content into the network, and the second one is the interest flooding attack, which intends to send a huge number of interest packets to the network in order to exhaust routers' resources. Since various technical issues are faced when attempting to enable vehicular data exchanges over TCP/IP, several researchers propose to bring NDN to connected vehicles. This figure illustrates an example of NDN-based VANET architecture. In this example, consumer 1 asks for the content. Given that the forwarder has already cached the requested content, it directly replies to consumer 1 without forwarding its interest packet to the original producer. The interests for content traffic/highway /A5/20 by consumer 3 is instead forwarded to the producer because the forwarder does not have this content. If in the meanwhile consumer 3 receives an interest for the same content from consumer 2, the request is aggregated in the PIT and the interest is not forwarded again. When the data packet arrives at the forwarder, it is forwarded to consumer 3, which forwards it in its turn to consumer 2 by following the PIT entries. Some of the benefits of applying NDN to VANETs are in-network caching, mobility and routing, and in-data security. So some of the security problems and remaining challenges that exist in VANET are as follows. The first one is the DOS, the denial of service. This is the most critical and well-known attack in the vehicular communication network. It is too worrying when it is related to urgent communications that can affect human life. The attackers continually send requests to the network with the intention of making services unavailable and preventing V2V and V2I communications. The second one is content or cache poisoning attack. In this one, a malicious vehicle sends fake content in reply to consumer interest packets, which will result in filling the CS of the consumer as well as the CS of intermediate nodes with false content, carrying out a data packet signature verification at every node. May be a good solution, but it increases the content retrieval delay. More investigations are still needed to tackle this issue. In the man-in-the-middle attack, as indicated by its name, this attack is based on a malicious vehicle in the middle of a communication medium, which intercepts all the packets and injects fake data, while the transmitter and the receiver believe that they are in direct communication with each other. In the case of communications over NDN, a cryptographic signature is used by the original publisher to sign the data packet. Therefore, any alteration or in the content will change the authentic signature. To achieve the goal of vehicular communications, which is enhancing road safety, forwarding emergency messages must be at the right time. In this attack, a malicious vehicle adds time slots and does not transmit safety messages in a punctual manner. Consequently, legitimate vehicles receive each message after the time they actually require it. This is a serious attack that needs more analysis, particularly when it comes to safety applications that require real time. Another attack is black hole attack. A black hole is a surface that contains a group of malicious vehicles that decline to engage in the network. They receive safety messages, but they do not forward them to other vehicles, which results in serious packet loss. An example of this attack is shown in this figure. Given that NDN makes the content at the center of the communication, it transfers interest packets and data packets without giving any importance to the nodes. Hence, this attack may not influence connected vehicles using NDN. In this attack, bogus information. This attack is based on fake information generated by malicious vehicles and sent to the network. The aim is to take control of other vehicles to the advantage of the attacker. For instance, it may ask legitimate vehicles to change the lane because of traffic jams, for example, and thus make its movement easier on the road. In order to deal with this attack, more research in NDN is needed and a robust trust model is required. So our research was carried about the security concerns in the NDN architecture, which is considered as a promising solution for the future internet and connected vehicles. Applying NDN to the vehicular environments makes the task more challenging and needs weighing up benefits and risks. In this work, we reviewed various attacks such as DOS, black hole, and man-in-the-middle, and we identified some issues that may be overcome thanks to the use of named contents and the integration of security at the packet level. Many challenges still needed and more efforts, and researchers in the field should give more importance to vulnerabilities in relation to poisoned caches and flooded interests. Thank you.